Okay, this video is going to be going over this circular motion worksheet, and it's likely to be a pretty long video here. I'm just going to go through each question one by one. Just feel free to fast forward if you want to get through this faster. Watch it at 1.25 or 1.5 speed or whatever it is you need to do. So some of these I'm going to be writing things out, and some of them I'll just talk about. So what's the difference between a centrifugal force and a centripetal force? So the centrifugal force is going to mean away from the center, and the centripetal force is going to mean towards the center. So when you're going around in a circle, you need a centripetal force to push you towards the center of a circle. But what you'll feel in your body is a centrifugal force that's pulling you away from the center. So once again, this is what you need to go around in the circle, and this is what your body's going to feel. This one's not actually a force. We call this a fake force or a fictitious force sometimes. So just adjust this camera a little bit. Okay, how can something be accelerating if it's moving at a constant speed? So we talk about cars going around corners or something going around and around in a circle at a constant speed, yet we have this formula for acceleration up here. So it can be moving at a constant speed and still be accelerating if it's changing direction. Remember, if you have a velocity, you have a speed and a direction for velocity. So either one of those changing is going to result in acceleration. And if you're going around in a circle, you're continuously changing your direction, and that means that you are accelerating. I feel like this focus is not very good here. Let's see if that's a little bit better. Okay, two cars are going around the same curve. Car A is going twice as fast as car B. How much more acceleration does car A have? So if we look up at this formula up here, the velocity is going to be relative or proportional to the velocity squared is proportional to the acceleration. So something going faster is going to have more acceleration, but it's by a proportion squared. So if car A is going twice as fast, it's going to have 4 times the acceleration. Acceleration. 4 times the acceleration for going twice as fast. That's because of this velocity squared term up here. Okay, two cars are going around corners. They're traveling at the same speed, so velocity is the same. So now we have twice the radius. So looking back at this formula up here, if you have twice the radius, you're going to have half the centripetal acceleration. So car C has twice the radius, so it's going to have, which car has more acceleration? So D has twice the acceleration, or you could say C has half the acceleration. Okay, good. So now we can move into some free body diagrams. And let's see, I might draw these on a separate sheet of paper just to get some more space here. Let's see. All right. So free body diagram for ball swinging. So now this time we are going to talk about a vertical circle. When I originally made this worksheet, I meant for this to be horizontal. Ignore gravity for this problem. Oh, geez. Okay, I wrote it there. Let's do something here. So first here's the free body diagrams number 1. Let's first talk about a horizontal circle with no gravity. And then we'll do a vertical circle with no gravity, which is kind of silly, and then with gravity. So a bunch of different things. So here we have the ball that's going around in a horizontal circle. So you're looking at it from a top view. If you're looking at it from a side view, then the ball would be kind of swinging around like this up to you. So what I want to do is I want to catch the ball when it's just coming towards you with a side view. So we'll draw the ball right there. And then the only thing that's happening is we have a centripetal force on it. It could be to the left or the right, just depends on what the perspective is. Here I was drawing the ball coming towards you like this. So the string is pulling on it towards the right. So I'm going to draw this right here, and that's just going to be a tension force, and that's going to be it. So that's the free body diagram for the horizontal circle with no gravity. The reason I did no gravity is because it gets tricky when you add gravity into the situation. Just as a little aside, in case you're curious, how the gravity would fit is if I had gravity going down like this, force of gravity, I would need to have my tension off at an angle like this so that my net force, the result of both of those forces, would point towards the center. And when you're swinging a ball around in a circle on a string, it's never exactly horizontal, right? It's always kind of angled down a little bit. So that's why I said to turn off gravity, because we don't have to do this kind of vector thing. So with no gravity, this is the situation. So let's do the vertical circle with no gravity. Vertical, no gravity. There's no reason to do no gravity in the vertical circle, but that's how I wrote it in the problem, so I'll solve it like that. So vertical circle, no gravity. Once again, we're looking at a side view. So I'm going to have the ball. Here's like a diagram of what's going on. There's the ball, and there's the center, and it's going around in a circle like that. Scooch this up a little bit. So we're going to draw the ball. Okay, so no gravity. Okay, now I can kind of understand. So it's going to really depend on where the ball is. I regret writing this problem. I think it's not the greatest problem because I didn't really say where the ball was going to be. So with no gravity, it doesn't matter. But when you turn gravity on, it really makes a difference for the free body diagram because you'll have gravity, going. Obviously, gravity is always going down. But let's say the ball is in this position at the bottom with no gravity. Oh, sorry. If the ball's at the position at the bottom, then we're just going to have tension pulling up like that. Force of tension. Okay, good. So that would be no gravity on the ball. If we add in gravity, so yes, gravity, then it's going to depend on where the ball is. If the ball's at the bottom down here, then we're going to have gravity going down and tension's going to be going up. The tension's going to need to be more than gravity because the net result of these has to be towards the center of the circle. If, however, the ball's, say, like at the top of the circle, then the situation's different because now I have a tension going down and gravity going down. And it's going to kind of depend on how fast the ball's going for the relative sizes of these. So not the best question. Like I said, I kind of wish I hadn't done that one. But okay, so number 2, free body diagram for a car going around the corner. And so once again, we're going to draw this from a side perspective. From the side perspective, we just have gravity going down. We've got a normal force going up. And then depending on which way the car is going, we'll have a friction force pushing the car towards the center of a circle like that. And then this is the centripetal force right there. Okay, turns out for number 3, it turns out to be the exact same free body diagram. So for a child on a merry-go-round, you're still going to have gravity, you're still going to have normal force, and friction is really the thing that's keeping them from sliding off, right? So you've got your cow going on the merry-go-round, and friction is the thing that's preventing them from sliding off. If there were no friction, they wouldn't be able to go around in a circle. So it's the same free body diagram for that one. Okay, moving right along here. Draw a free body diagram for a person walking inside a rotating space station with artificial gravity. Here, let's move this up a little bit. Okay, which force is the centripetal force? So this is once again kind of a tricky perspective to get right. You could really have any angle that you wanted whatsoever. So if here's my rotating space station, let's see if I can make this look okay. That wasn't such a good job. But anyways, there's my rotating space station rotating, in maybe this horizontal direction. But maybe you want your rotating space station going in the vertical direction, so it's hard to tell. And I'm going to grab a person, say, from right over there. So from that side view right there, the person's walking like this in the rotating space station, right? Or maybe they're walking like this on this side or wherever they're going. So if I chose this spot over here, I'm just going to get a normal force, and that's it. There's no gravity, there's no tension, there's nothing else. Now, there would have to be a little bit of friction from like side to side, preventing them from sliding, but friction is not pointing them towards the center of the circle. This is the centripetal force, and that's it. But really for this problem, you could have done any direction you wanted to do, right? You could have gone like this if the rotating space station were in this direction and they were at the top, right? Maybe your rotating space station is sideways or whatever. So any free body diagram where you just have a normal force like that is going to be good for that one. Okay, for number 5, draw a free body diagram for a person riding in a Ferris wheel at the top of the circle. Okay, so we'll just do that one down here. They're at the top of the circle. Of course, they're going to have gravity going down like this. Now, if you're in a Ferris wheel, you're right side up, so you're going to have a normal force pushing you up. But what I need to have happen here is I need the normal force to be a little bit less than gravity. Why? Because I need a net force towards the center of the circle. That's going to be the centripetal force. So really, it's gravity here, and some of gravity's effect is being taken away by this normal force. But we can also say it's the net result of both of these forces that's going to result in the centripetal force. If you had a free body diagram where they were balanced, or you had gravity and the normal force were equal to each other, then this would be a situation where I would have equilibrium, And in equilibrium, you can't be accelerating. And yes, you're not speeding up or slowing down when you're on the Ferris wheel, but you are accelerating because you're going towards the center of the circle. Remember, we have centripetal acceleration. Okay? And then lastly, we'll just do it over here. Free body diagram for a person on a roller coaster loop upside down at the top of the loop. Okay, so it could be a couple different things here, but there's my person. There's gravity going down right there. The reason I say it could be a couple different situations is because this could be enough. If you are barely going over the top, here's my roller coaster loop. There's my roller coaster car. Okay, wheels, whatever. Okay, so if you're barely making it over the top, then gravity might be it, and gravity would be the centripetal force. If, however, you're going really, really fast, or somewhat fast, you'd have some kind of normal force acting on you. The faster you go, the more normal force you need in order to make it over the top. So if you're going really fast, then you might have a really big normal force. And remember, what that's going to feel like for you is you're going to feel really stuck into your seat, right? So the centripetal force here is the result, once again, of both of these added together. So it's the net result of these things added together that's going to produce the centripetal force towards the center of the circle. Okay, all right, moving right along. Now we're going to do some calculations. You hop in your Porsche, you go out for a test drive, 25 meters per second, you experience 3 Gs of acceleration. So 3 Gs, we're going to call that 30 meters per second squared, and that is your centripetal acceleration, right? Our formula for centripetal acceleration says v squared over r, and we know your v is 25 meters per second. So I'm going to drop the units just to make things work out easier here. So 30, that's my centripetal acceleration. 25 is my speed. 25 squared divided by r. And then I'm hoping that your algebra is just getting better and better and better. And one-step algebra, you can just go, r is going to be 25 squared over 30. And then we'll do that here. 25 squared is 625 divided by 30, 20.8. 20.8 meters. The radius is going to work out in meters. Okie doke. Find the centripetal acceleration of a soccer player running at 8 meters per second around a corner of 1.5 meters. Okay, not so bad. Formula for centripetal acceleration, v squared over r. The v is 8. I'm going to drop my units once again. 8 squared over 1.5. So that's 64 over 1.5. 64 divided by 1.5, and we get 40, we'll just call it 43. 43 meters per second squared, and turning that into Gs, we're going to get 4.3 Gs. Okay, well, that's pretty unreasonable for a soccer player to run around a corner and get 4.3 Gs. But, okay, so didn't make up such good numbers for that problem. Let's go on to number 3 down here. Okay, you're on a merry-go-round. You feel like you're getting pulled to the outside of the ride with a force of half your weight. You estimate the radius of the ride to be 8 meters and your mass is 70 kilograms. Find your velocity. So we're working with this formula, v squared over r. We're given 8 as the radius. We're looking for this. We weren't given this, and that's what we can kind of reason out from the problem. And if you're being pulled to the outside with a force of half your weight, that means you're experiencing half a g. So experiencing a force of 1g is like experiencing 1 time your weight. I need to focus this again. Yeah, that's a little better. So if you're experiencing 1g, then you're experiencing a force of exactly 1 time your weight. So experiencing a force of half a g is going to be half of your weight. So now we know that the centripetal acceleration is going to be half a g. That's 5 meters per second squared. So we're just going to set this up. 5 equals v squared over 8. Oh, it looks like the mass is sort of irrelevant there. So I threw in the mass. There's a way to do this with forces where the mass could be included, but in this case, we don't really need the mass. And then now I'm going to get v as the square root of 40. And square root of 40, 6.3. And meters per second for your units on that. So there goes the lights in the classroom. I'm going to turn those back on. Okay, so where are we now? Okay, so now here's these RPMs problems. And I say, side note, some physics problems use RPM to describe the speed of something spinning. We talked in class about how to go from RPM to velocity. We didn't talk in class too much about it, but it was on this lab that we were doing. So I'll just sort of share with you the idea about how to get velocity from RPMs. So if you know your RPMs, your velocity is going to equal however many RPMs you have. You're going to multiply it times 2 pi. You're going to multiply times the radius, and then you're going to divide it by 60. And that'll get you your RPMs. Sorry, that'll get you your velocity in meters per second. So I'm not going to ask any quiz problems about this because it's just one extra step and we didn't really talk about it too much. But RPMs, it's not that hard to deal with as long as you can kind of know this situation. Make sure that your radius is in meters. And this 60 is in there to go from the minutes to the seconds, revolutions per minute to seconds. So if I look at problem 4 here, tennis ball is swinging around a horizontal circle. The string has length of 75 centimeters. The ball has a mass of this. Ignore gravity. If the ball is swinging at 40 RPMs, find the tension in the string, right? So just the quick free body diagram, tension is the centripetal force. So what I can write here is I know that the force of tension is the centripetal force. And my formula for centripetal force is just m times v squared over r. So our goal in this problem, we have mass and we have the radius. We just need to find the velocity. The mass over here, just so we know, is given at 350 grams. That's going to be 0.35 kilograms. Okay, and then the radius is given in centimeters, is going to be 0.75 meters. So we just want to make sure we're using the right kind of units here. So let's find the velocity. We're going to do this thing up here. So the velocity is going to be 40 RPMs. So we're going to take 40 RPMs times 2 times pi times the radius, which is 0.75, and then we're going to divide that by 60. So it was 40 times 2 times, I'm just going to do 3.14 for pi, times 0.75 divided by 60, and I got pi again? How's that happening? 2, 40, 60. Okay, I guess that makes sense. All right. 3.14 meters per second. Because this 40 and this 60 are related together by 1 1/4, and then you take away that 1 1/4 by, or sorry, 1 1/2, and you take away that 1 1/2 by this 0.75 times 2. So you get the pi back. So like this times this is 1.5, and 1.5 times 40 is 60, so that's how that worked out. That just was kind of weird for me for a sec. Okay, great. So now what are we doing? We're looking for this tension right here, and that's going to be m times v squared over r. 0.35 is the m, the v is 3.14, square that, divided by 0.75, and what do we got here? 0.35 times 3.14 squared, and divide that by 0.75. And the tension is going to be 46. And that's going to work out in newtons, because all of our forces work out in newtons. Okay, so B on this problem says, if the length of the string is doubled but the RPM stays the same, what is the tension in the string? You'll need to recalculate the velocity. Okay, so we got to recalculate the velocity again. Here, let me move it down here. So the length of the string is doubled. So now for our velocity, we're going to have same thing, 40 RPMs times 2 times pi times the length of the string is doubled, 1.5, and that's divided by 60. And since all we did was double the length of the string, we're going to double the speed right here to 6.28 meters per second. Good. So then we have to do this problem again, this whole thing again with a new, the RPM stays the same, but the velocity is different. So we have 0.35 times, now my new velocity here, 6.28 squared, and divided by my new radius, 1.5. Clear, 0.35 times 6.28 squared, and divide that by 1.5. And this is 9.2, oh, sorry. Something looks funny there. Let's try that again. 0.35 0.3, oh, that's because I did it weird. 0.35 times 6.28 squared. And now I divide that by 1.5. 9.2. So this one looks funny now. Let's do that one again. 0.35 times 3.14 squared. Oh yeah, that was way off. Divided by 0.75. Huh, 4.6. Okay. And then this one's turning into 9.2 because it turns out to double it. Okay. So, gosh. You know, I'm just going to, I told you I wasn't going to do the RPM problems, so I'm just going to skip this one. Oh boy. I'm going to skip this one here because it's just taking up too much time. So we'll skip that because it's having to do with this RPMs. Should we skip it? I don't know. I'll do it. It's just a long video already, so just going to make it longer. Already 20 minutes, but we'll just keep going here. Okay, so you get shrunk down to the size of a pickle, so there's your mass. Taking a ride on a record player, the diameter, okay, is 0.25 meters. So I'm going to get the radius as 0.125 meters. And we have 33 RPM, and then the mass is 0.1 kilograms. So how much centripetal force do you experience? So this one, the free body diagram is gravity going down, normal force going up, and force of friction. And we are looking for how much centripetal force do you experience. Remember, centripetal force is m times v squared over r. To get the v, we need to do this RPM calculation again. So the v is going to be 33 RPMs times 2 times pi times the radius, 0.125, divided by 60. Plug that in. Clear. 33 times 2 times 3.14 times 0.125 divided by 60. So this is giving me 0.43 meters per second. Oops. All right, so now how much force do you experience? That's going to be this right here. That's the force. So we get Fc equals 0.1, that's my mass, times my velocity squared, 0.43 squared, divided by the radius, which is 0.125. We'll do that. 0.1 times 0.43 squared equals, divided by 0.125. So that is 0.15 newtons. That's how many newtons of force you need. Now remember, my friction force is mu times my normal force. Normal force and gravity are equal to each other. So this is mu times m times g. And that is this force right there, 0.15 newtons. So I know m, I know g, and I just need to find mu. So mu is going to be 0.5 divided by my mass, 0.1 times g, 10. The 0.1 times 10 cancel each other out, and I'm going to get 0.15 for my coefficient of friction that I need. Okay, phew, moving right along. Vertical circles and loops. All right. A dog is a dog of mass 15 kilograms on a swing in a playground. The swing has a radius of 15 meters. The bottom of the path moving at 5 meters per second. Find the normal force on the dog. Okay, so free body diagram time. We've got gravity here, and we've got normal force there. So I'm going to make my normal force bigger than gravity. Okay, and now what has to happen here? I have all these things. I have my speed, I have my radius, but I need to do a little bit of thinking here because what I need is I need to know the net force. The net force is going to be my centripetal force, so the sum of those two things together. Since this one's pointing up towards the center of the circle, I'm going to call that positive. So my net force is the result of these two added together, but they're really subtracted because they're going in opposite directions. So I'm going to say normal force minus gravity is going to equal this centripetal force. That's mv squared over r for centripetal force. I'm looking for normal force. Find the normal force on the dog is what the problem says. So just algebraize, normal force is going to be mv squared over r. So I'm just adding this to this side. Add this to both sides of the equation, plus force of gravity. So now I got it. This is mg, by the way. So this is mv squared over r plus mg. That's my normal force. Now let's just plug in the numbers we have. Normal force. Let's see here. Equals m 15 times v 5 squared divided by r 5. Well, that's easy because that just turns into 5. And then 15 times, oops, that's not an equals, that's a plus. Plus 15 times 10. So 5 squared divided by 5 is just 5. 5 times 5 is 75. 75 plus 150 is 225. 225 newtons is your answer for that one. All right. Snowboarders moving through a half pipe, which can be thought of as a semicircle radius of 4 meters. Okay, cool, 4 meters. Experiencing 3 Gs at the bottom of the pipe, find the velocity of the snowboarder. So what we're going to do here is kind of set up the same free body diagram. We've got gravity, we've got normal force, but, okay, let's make my gravity smaller than the normal force. Good. If the snowboarder is experiencing 3 Gs, that's like the overall result of, you get 1 G from gravity, and then you're going to get 2 extra Gs from this normal force right here. So really what's happening is the acceleration of the snowboarder is really going to be 2 Gs, and then the gravity force is going to add in the other G to get a total of 3 Gs. So right, you have to remember when you had your pocket lab, here, let me grab the pocket lab. Okay, so when the pocket lab was just sitting here, it's already experiencing 1 G. So whichever direction you're going in, so there's the plus y direction. So if you're on this swing right here going through this, it's experiencing 1 G just by itself. So the extra 2 Gs is going to be from the acceleration going through this circle. So what we really want is we want the centripetal acceleration to be 2 Gs. That's 20 meters per second squared. And now we're just going to say that 20 is going to be v squared over r. We know the radius. V squared over 4 is the radius. So v is going to be the square root of 80, which is going to be pretty close to 9, but let's just see what we got here. Square root of 80. 8.9 meters per second. So the tricky thing about this problem is realizing that when you're in a vertical circle, one of the G's that you're experiencing is going to be from gravity, and then the other G's are going to be from your acceleration. Okay, on the next run, the snowboarder has twice the speed. How many G's will they experience? So if you're experiencing 2 G's at one speed, you're going to experience, so 2 G's from the acceleration, twice the speed is going to bump that up to 4 G's. So the acceleration is going to go up to 4 G's, but the total is going to be 5 G's. So the acceleration is going to give you 4, and then gravity is still acting on you, so you're going to have a total of 5 G's out of that. That would be a lot, by the way. Okay, and then this is the last problem, and I haven't gone over this in class. There's a video I might share with you. I might or might not, but maybe this is not going to be on the quiz, but I'll just show you what this means. So we can talk about positive G's, negative G's, 0 G's, or neutral G's. So what that means is if you are sitting in a chair, just regular sitting in a chair, and nothing's going on with you, you're experiencing gravity's pushing you down and normal force is pushing you up. So you're feeling this normal force pushing you up, so you're experiencing you're experiencing 1 G, but I would call that neutral, because you're not really accelerating at all. So just sitting in a chair, you're experiencing 1 G, and that's like neutral G's. So anytime you're just going on a flat surface at a constant speed, that's going to be neutral G's. So it could be neutral G's here because it's kind of flat. This is like you're going up a slope, but this would sort of be considered neutral as well. But then definitely this one would be neutral. Neutral G's over there because you're just on a flat surface. These might be a little different because you're kind of going uphill, and this is like a little bit of a part of a circle, and this is a part of a circle as well. This one I might consider neutral G's as well, or maybe 0 G's here. If you're going on a 0 G's, could be 0 G's there because you're going on a slope. Turn the lights back on. Okay, so this part B right there, that's going to be positive G's. So you're going to have a normal force pushing up on you really hard right there. You're going to feel really heavy, and your acceleration is up towards the top of your head. So this is going to be positive G's in this position right there for B. Part C, it could be 0 if you're going at just the right speed, or it could be negative G's because you're going in this circle like this, and you're going to feel like you're being thrown out of your seat. And that feeling like you're being thrown out of your seat is the result of an acceleration down, and that's going to be negative G's like that. In this one, you're feeling an acceleration this way because your body is oriented sideways. This is going to be positive G's over here. This one, it's tough to say. I think that this one could be neutral, or it could be maybe a little bit of negative G's going up over like that. So we may or may not talk about this in class. Just kind of depends on if we have time or not. All right, extra long video. Hopefully that was helpful for figuring out how to do some of these problems.